Hello, gentle readers. Today is May 4th, 2025. In Logos 2000, 21st Century Foundations today, well, I thought to continue with Quine a bit on word and object and kind of segue from that into Descartes' Meditations. Yet there's quite a pile of the differential equations books piling up, and then also as with regards to what the reading material recently is that I've been reading about computers and the implementation or the theory of computers. So I thought I'd go through some of these books here that are considered kind of useful in the design and development of information systems on computers, and particularly kind of with regards to the operating system and these kinds of things. So let's take a look at some of these works and see what we might find a little bit today from these works, and hopefully what I can relay to you as some kind of acquired knowledge developed over the time of from when I first kind of acquired these books and over the course of the decades that I have been a professional in this sort of field of software development and computer science. That this way we could get into maybe some of the trails up into the tracks, up into the vast bog standard, utterly common, ubiquitous commodity computing of the day. So these days, when you get a computer chip, it's like a PC or a phone usually. This is a personal computer. And then in terms of the data center or nodes, those are also largely commodity. And as of after very usual instruction sets that according to their very common architectures, that these days there's sort of a mix of the advanced RISC machines or ARM and the AMD and Intel after x86, the x86 64 complex or CISC instruction set coding vis-a-vis reduced instruction set coding, those being the chips proper, and then with regards to the North Bridge and South Bridge, or as with regards to the bus, that these days is very standardized or just so ubiquitous that for something like this I2C or the bus protocol, that after the totally ubiquitous extended firmware interface or universal extended firmware interface starts up, that this sort of totally ubiquitous bus architecture kind of arrives, one for the ARM side and the other for the AMD 64 or Intel side. That then in terms of those, and then the virtualization environments, which is kind of where you run a computer on a computer, about the scheduling of the resources, these computing resources. As with regards to the bus and contention on the bus, that being the combined routes through the information pathways on the chip and the board, or the integrated circuits of the chip and the board. Then there's the ideas that the computing of the today is very much simplified in terms of these environments and setting up a flat namespace after the universal extended firmware interface, and that's kind of written in a language called Forth, F-O-R-T-H. And then as with regards to after that, whether getting into an executive or scheduler on these usual, what used to be called, say, PC or PC 2000, in the year 2000, it's 25 years later, that they have the ideas of the initialization after power on cell test, a very common thing. And then what used to be called a BIOS, a basic input output system, and its cataloged interrupts, meaning codes that led to board level instructions. And that today, then, with regards to almost the totally ubiquitous of the universal serial bus, and it has been for these decades since the parallel ATA or attachments and peripherals and the parallel and the serial and those sorts ports and protocols, and their synchrony on the board of the PC. came instead to be as with regards to the universal serial bus and its synchronization methods as with regards to interrupts and then the communications between particular chips as regards to common memory locations, and then also as regards to data flowing on the bus between various components like the network interface cards or NICs, with regards to UARTs, UARTs, those being briefly caches or buffers, reflecting how I/O, input and output, makes throughput on these machines. That one of the remarkable things is that from whence there was a really very, very wide sort of variety in the implementations, it's gotten a lot simpler in many senses just because the commodity PCs and other computing units, whether it's personal computers like laptops or desktops or often cellular devices or pads, the phablet or tablet or handheld device. The chipsets and the boards and the protocols of buses with regards to design and implementation of an operating system or scheduler or executive is much simplified. It's larger in a sense, yet much simplified. And then that being true for many commodity technologies, and is also kind of evidenced in the smaller kits available like Raspberry Pi or some other means to make briefly general purpose computing systems with regards to the CPU, the central processing unit, RAM or memory, random access memory, out to the disk, and then with regards to I/O, that these components are just remarkably tame in a sense, ubiquitously commodity, an embarrassment of computing resources. That then with regards to certain peripherals like graphics adapters extended or floating point units, these may variously have their own sorts, briefly ecosystems. And yet at the same time, there's almost always a possibility of still getting out of it stuff like VESA, VESA, and VGA, and super VGA, and extended VGA, as with regards to what's become this new like WQXGA. Not really new in the sense that these are standards that have been around for 10 or 15 years. Then it was with regards to the artifacts of the graphical display, for example, fonts in these ones. They're, again, largely unchanged for at least 5 or 10 years. Then that getting into these books and computers is possible to kind of get the fundamentals and then have a lot that can be applied quite sort of directly, because it's no longer so necessary when considering to write something like an operating system or scheduler or the executive in the usual kind of real-time sense vis-a-vis the time-sharing sense, and with regards to preemptive and or the cooperative and competitive models of multi-threading, multitasking, and these kinds of things, and for virtualization in the hypervisor and these kinds of things. With regards to usual notions of an operating system's designation of naming a directory of resources and the various controls so associated beyond mere interoperability with regards to permissions and the Orange Book, say, or these various kind of standards that can be so applied. That then we'll take a look at some of these books and get an idea of kind of what's going on with them. As with regards to that, then the idea is that even though these books are decades old, 60 years old, that they are kind of still in effect today. And indeed, some of their installations are still in effect today. So it's kind of, it can kind of be some remarkable reading. That then for kind of the period of the greatest explosion of development, or we might call the era of the PS2, or you know, like when the IBM PC became a thing, and then that Windows operating system became a thing, so IBM didn't get sunk by antitrust in all these years, and then that all the developments of the mass market and peripherals and systems have kind of come and gone to this later model of invention where the first one barely works, the second one is overly complicated, and the third one is kind of a simplistic compromise. It does end up being so that although the computers are incredibly large in terms of their offsets, like from the 32-bit after that to the 64-bit, and the usual chips these days that cost $5 or $10 a piece, and RAM in the memory modules that's on the order of gigabytes and more for thousands of terms in reduction cost since 25 years ago. That let's take a look at these books and get an idea of kind of what might be so simulated from their context, and as with regards to what that may well portend for someone who'd like to consider the design and implementation of computing architecture from first principles, de novo, as with regards to what's provided as just an adapter or the idea of the surrounds. So an executive basically runs the computer as one big program. The scheduler schedules the resources in so whatever manner, and then the operating system basically provides, there's the idea of interactivity between the data plane and the control plane. So this first book here is called Digital Computer User's Handbook by Klerer and Korn. This is from about 1965. It's printed by McGraw-Hill. And what it's about is that in the days of 1965, these books were part of McGraw-Hill handbooks, for example, of mathematical tables and formulas, process instruments and controls, semiconductor electronics, radio engineering, astronautical engineering, Lang's Handbook of Chemistry, Electronics and Nucleonics Dictionary, Radio Engineer's Handbook, and these kinds of things. That the authors Klerer and Korn, PhDs, have arrived at this 1976 imprint called Digital Computer User's Handbook. So it has many contributors here, and then what they're talking about is, for example, algol and various computer systems of the day. And so this is a computer science book largely. It gets into like sorting and searching and ways to set up linear analysis, and that in the computer science that it gets into like systems of equations and tables of derivations, and these ideas of solvers and the estimates and their bounds and their error estimates that are bounds, and the numerical methods largely, and various other of linear algorithms, a quite grand glossary, say, of sorting and merging terms here that is about tapes and collating and sorting. And these being kind of, that sort is one of the fundamental algorithms of doing work in computer systems. And with about keys, for example, the key is defined, also sequencing key criteria, sequencing criteria. The fields in a record which determine or are used as a basis for determining the sequence of records in a file. So this with regards to the sort key, and vis-a-vis the relational key of the relational algebras and databases and these kinds of things. Polyphase merging, a technique used in a sort program that merges strings of sequenced data. Given T work tapes, merging is performed at the power of T minus 1. Effective power of the merge varies between T minus 1 and T over 2, depending on the amount of input data and the number of strings. Talks about some descriptive properties of algorithms and results, and stability and astability, and a kind of anti-stability in terms of the sorts in regards to what goes in and what comes out, and if you sort it again, it's the same. And I mentioned various systems like COBOL. Here it's getting into data characteristics, the volume of data, fixed or variable length records, record size, randomness of data, and the number of keys. These are still pretty much usual, and they mean the same thing, and they are the terms from the algorithms of the day. buffering ability, the necessity when something can't be in real time resources, that it must be kind of, via divide and conquer or otherwise the design of the algorithm, how it can be memory size, independent reading and writing. So that's the I/O of these design of these merge and sort systems. Merging and sorting of being an article here. The stack machines, of course, is for the usual notions of the von Neumann or Harvard architectures, usually these days always Harvard architecture, and the stack machines are the towers of Hanoi and all this kind of stuff that after something like a notion of general purpose universal computing like the Turing tape, that's usually used mostly for classroom studies vis-a-vis what may be a stack machine, what are finite state machines often. And then with regards to the architectures and the coherency and the proximity of the data from the chip, where it's the most alive and fastest and can actually be evaluated in terms of each other, on out to through the caches, through the L1, L2, and L3 caches, and then out to RAM on the bus with regards to direct memory access and vector input-output or scatter-gather that allows that large amounts of memory can be moved with one instruction. And then the idea of that sooner or later then that all goes through the central processing unit. These are just kind of usual considerations that have, as far as the process model goes, not much variation at all in many models of general purpose computing. List processing languages, the allocation of list storage, or just here it could be just considered arrays of terms or addresses in memory, and the languages, values and parameters, procedures, precedence of operators, and Boolean algebras, or sequence. In the instructions have an order. Blocks. Now, the block is a very kind of abstract term, and it just means a block. It's got sub-block matrices. It's a block of data. It's a block of text. It's a block of code, and so the block is a common structure that isn't so much given usually a first-class term in modern computing languages and programming environments, but it very much so was a fixed amount of stuff in these kind of original systems. Conditional statements. This is the procedural vis-a-vis the functional, where in the procedural things start at an entry point and proceed, and then the procedural, and whereas in the functional that it's as things happen and then they arrive at calling a function, and so kind of fan in and fan out type of thing, and those kind of still reflect one overall procedural and functional program that if else and while do and for each, and these ones are still very much so the common idioms for conditional flow of control and such. Then as regards to exceptions and the scope and the stack, when it is so that the model of execution is well defined, and that defined behavior thus is a goal of computer science, and then as regards to the readability and comprehensibility to comprehending or reading code, that it's named well and matches very common terms, and so that quite so usually it's so put together. So here's kind of after this algorithmic compiler design bit from Grau, Garau. Then what there is here is an index of manufacturers of the time. And so this kind of lists all the computers that were lived in the world in 1967. And so it has kind of like a chronological listing of vacuum tube and solid state computers manufactured in the United States and installed between 1951 and 1965. Starts with the UNIVAC and some IBM and Burroughs. The IBM UNIVAC, LGP, ALWAC, the IBM RAMAC, UNIVAC, Philco, Recomp, NCR, and RCA, making computers up to 1959. General Precision, Monrobot, Philco, General Electric, General Precision, RPC, Packard Bell. So in 1960, these were the computers in the United States. The computers. Through 1964, there's a good 40, 50 of these these manufactured computers. So not all, exactly necessarily all the installations they had, but all the installations that there were. And kind of some monthly amounts or their costs, and then their parameters and properties, any one of which has that all of these could be run at one time in one computer today. You could kind of make an emulator, each one of these different kinds of computers that can all be run today. Here's from the Netherlands, they had Electrologica, or from the Svenskers had Saab, the Toshiba, Boll, Nippon, Oki Electric. Many computers popping up here. Hitachi, Matsushita, Mitsubishi, Nippon, Fuji. And then getting into the Italian, there's this Olivetti. And then we get into like Boll and the French. Siemens, Telefunken, Zusi, Boll, NCT, ICT, Orion. And this is the English stuff though. English Electric, Elio Marconi, Elliott, and the Ferranti from Canada, Regner Central and Gear from Denmark. These were all computers before 1965, say. And all the manufacturers of these in the world. Control Data, Bunkeramo Collins, Control Data, Digital Electronics, of these being general purpose computers manufactured. NCR, and then they'll have some, they might also illustrate some that were designed in the former Soviet Union in this, or with regards to those being very controlled things, and digital computers and analog computers, and that they're kind of just categorized in terms of their word size, processor speed, input-output channels, disk storage, magnetic tape, other features like program interrupt, index registers, indirect addressing, or the virtual memory, and then that also with regards to combined facilities with regards to the virtual memory, the manipulation of particular bytes, and input-output streams of the console, and then different softwares like an algebraic compiler, a business compiler, and those being kind of given as the only software that they had. So this book, when I found it, it made me happy because it was a pretty thorough survey, both of computer science and the installation of computers worldwide as of a time and place, and helps to illustrate so much has happened and gone on since then, that today it's possible for the single person or a small effort to direct a large amount of information processing ability. Maybe not large in the overall scope of all the ops in the world, but yet it's still quite so large compared to what were all the ops in the world. With regards to multiplexing and the digital to analog measures, small general purpose computers, typical cathode ray tube indicator characteristics. Cathode ray tube, of course, is a sort of obsolete, means that after the invention of the cathode ray tube or the television, that in terms of raster logic, the back and forth and rows and columns, pixels, picture elements, or the vector displays, which actually drew the line every single time to make those, those are quite commodity today, and very much so uniform, and all these kinds of things. It has a great index of terms, and reflecting it all together, this is quite a thorough handbook of computing, with regards to the story of the implementation of algorithms and via hardware and software for the day with regards to microfilm and information retrieval. That's become quite a thing. You've probably heard of search. It's information retrieval, and an interface and mathematical topics, the organization of data and indexing, all one big sort of sorts. That batch processing and then simplex and linear and nonlinear and integer programming, and ideas that would result in the same things as neural nets, all this was textbook by 1967. So, pretty good little book. I've had that for some years, and I've read it a bit. But I got more of my concrete mathematics from, at least at one point, having not done all the exercises, at least having read through Donald Knuth's The Art of Computer Programming, volumes 1 through 3, and then later there was a volume 4, the fascicles that came out about it. So much about tapes, with a great fold out of how it's possible to operate 10 different magnetic tapes and to change them back and forth to make a sort that's larger than resources than a divide and conquer or serial algorithm could achieve, to make it so that then in the concrete mathematics, it all sorts limits and bounds, and the terms would have to be kind of figured and planned out in what's called concrete mathematics, which is also after another great book called Concrete Mathematics by Graham, Knuth, and Patashnik. That's what I would have read, compared to those being computer science fundamentals in terms of sorting and stacks and finite state machines and then for flow machines. And then with regards to architecture, that it's got process models or resource models, and so it's pretty simple to begin to describe them. And then for program models, they have entry points and conditions of exit of the state, of the data, and the scope and the visibility of data to other data, of the coherency and the proximity and the affinity, those being terms about like what's where on the chipboard and bus. That with these kinds of terms all put together, then it's possible to have a pretty thorough account of a top-down view of then what results of bottom-up development of the computing, from the ideas that these days it's after power on self-test, and let's see if I can boot from the network if it shows up with TFTP. Let's see if I can boot from USB from whatever shows up as a mass storage device. Let's see if I can boot up from the storage in this and that. The boot sequence that then as regards to universal extended firmware interface, and whether these days it's possible to write the operating system after that using the services that the extended firmware interface provides as the hardware extraction layer over the firmware, because otherwise it requires getting down to the timing. And what's so necessary in the timing is that the actual chip ticks have to drive the memory refresh, because the way random access memory is designed is it needs a constant cycling to keep it coherent, and whereas everything else on the board and chip, if it's not working or doing anything, it can kind of like power up and down through these various levels of power, that the system services of the extended firmware interface include ACPI for the advanced control power indicators, or ACPI power, and then there's SMS, which is like system management services and these things. There's a very few things to do with the control registers, which define how the chips will operate and what instructions they're pointing at, what they do, that it's not so hard-coded. Then with regards to various modules like the trusted platform computing, or encryption modules, or signature modules. And then otherwise with regards to the hardware and these kinds of things. That's my kind of comprehension and understanding of that the extended firmware interface then provides a really simple way to then have basically a functional computer. It is a little operating system, and it does have kind of naming in a directory of the resources. That's also not necessarily needfully employed when it's possible that the actual writing to the bit accurate and then the clock accurate isn't so difficult to make the clock accurate codes, which is of course very complicated and very involved, very difficult. Yet at the same time, not so much as it once was. There was a time when all the different memories, for example, would have different means and modes of access and their addressing, and that the chip would be in various different modes and have to get into protected mode. That these days everything kind of lives in protected mode, and that but yet real mode is still kind of a thing, and it's just quite a bit more complicated to write to, because that's where the variations have been hidden in the hardware abstraction layer. Yet today, though, the extended firmware interface, or the UEFI, after the extended firmware interface, makes for that the system services, the services, as they start, are kind of in place. Not everybody wants all those anyways, and so then, in particularly apparent in some of the smaller chip things, like it's just like a $5 chip and a $5 NIC and a $5 piece of memory that's bigger than, you know, a $5,000 Pentium from 30 years ago. That these are the kinds of things to get into a little bit. This book is Raphael Finkel's On Operating Systems Vade Mecum, a walkthrough. So this kind of talk is like an OS walkthrough a bit. But this book, On Operating Systems Vade Mecum, was, if I'm pronouncing that correctly, is a walkthrough of operating systems. And so this fellow saw the development of the field, and this was published in 1986. And he starts talking about basically the time of that 1965, and he introduces I/O and models of computing, and then some principles. These days are a little bit different from this book, but they're still kind of as from this school. And so this is kind of a very, very usual school in the American. This is out of Wisconsin. So this is kind of the Wisconsin school. And Finkel starts, and then he describes, like, in very readable and thorough kind of wording, how to approach the concepts and the principles of the operation, and then makes definitions to help define what is an operating system. And then he gets into how to get these things. So chapters look stuff like an introduction, time management, the scheduling and the aspect. He gets into a lot of the details of, like, how to formalize when you have a model of actors and a model of resources, how to allocate these resources to the activities so they can be accomplished, while yet that not only may the activities be unable to operate, not given the resources they need, but they might also not be cooperative in the sense of being intentionally cooperative, and indeed maybe intentionally antagonistic towards cooperation. So that gets into the usual ideas here of the preemptive multi-threading, context switches, and these kinds of things, vis-a-vis the overall cooperative multitasking and multi-threading, which, while it may be possible to build that into the languages then, which result to object files, the machine object files being the list of instructions or list of data or list of text, that the language, pretty much according to the portable operating system interoperability guidelines, that being kind of like what most people think would just call that Unix. It has that to reach some of those, then the high level, way above the operating system, for both the system libraries and the tools, which result executables and their process model and resource model, that it can be done a bunch of different ways. And then this book basically reflects the implementations of general purpose computing and with software, say, and vis-a-vis descriptions that aren't just general purpose to load the objects and then to map to their entry points and to link the objects variously by the library linking of the programs into memory, that then to run them, to execute and run the programs. So that's kind of about time management. And then chapter 3 is space management. Time and space, of course, are just kind of the general resources. If it's not dollars and it's not watts and it's not eventually like clock time, calendar time, then on each of the CPUs, it's time as CPU cycles executing operations on the registers, and then moving those in and out of the space of the things. Talks about the clock's non-preemptible resources, transput. The author defines transput as input and output. So when you think of a process model, sometimes that's output and input, and sometimes it's input and output. Because if you think of it, the inside of a program, it gets input and writes output. But if you think of the boundaries and between programs, then there writes an output and makes an input. So there's kind of both models of transput and throughput to go with input and output, or output and input, those reflecting the serial transmission of data. And then that could be also like wide, or the parallel transmission of data. And then with regards to the simplex, or one way, the duplex, or one way, two way, one at a time, the full duplex, both ways at the same time. Transput. File structures. So above the resources of storage is raw and just a uniform space, like random access memory kind of is, and gets loaded and filled as the computer starts and then runs, and is a constantly kind of maintained resource. And files are the durable resource generally. The idea is that a file is a world of this computer. It's naming a directory of resources of data, and then that's as at rest, and that then there's certain guarantees or the notions for well-defined behavior of the atomicity of file system operations, that among all these what results system calls, that any function can make system calls, and then otherwise each function is living in a land of libraries in its own code. That the file is just an example of an abstraction of this. What's the durability of the resource, and so that's one of these considerations in the operating system design. Then is what kind of files to support and how to support them. The user interface, the command interpreters, is chapter 7, section 1. Interactive programs, utility programs, perspective. And then chapter 8 is concurrency, and then chapter 9 is cooperating processes. And he talks about things like semaphores, software interrupts, pipes, ports, the semantics of read and write, multiprocessors, and then networking. Networking begins to get a lot more of an idea going on, because these computers lived in their own little world. And so then with regards to networking, these days everything is pretty much ubiquitously networked. And you can design programs on the box to just think they live on a network. And then that way also it's possible to just make programs kind of run designed for living in networks, that they don't have to use the networks at all. So it becomes that the matters of networking are merely inter-process communication. And so that gets into the design and idea of standards for then what goes into interoperability. And so these are usually on the internet, as of according to the Internet Engineering Task Force's requests for comments, that since the time of the internet have been the working medium of open cooperation between entities that are good actors on the network, as not to be considered the same thing as proprietary standards or collusive standards, and these kinds of things. So this is a pretty great book, and he's got his principles, and he explains a lot of the trade-offs and then decision-making procedures. Talks a lot about Dijkstra and Hoare, Bring Hansen, but about the inventor of Pascal, Nicholas Wirth. He gets a lot of praise from the author. Lamport. And then here's talking about the dining philosophers, where the dining philosophers is a usual thought experiment trying to help explain simply setups or situations in concurrency. And then as with regards to models of callbacks or interrupts or polling, and as regards to models of concurrency and co-processes in the parallel. He's got a great little glossary. Activity, an executing entity, whether a process or kernel, task an interrupt-driven procedure, or a DMA transfer. See, already this kind of gets into some things. It's like, well, we've designed our system so you can think of it as a universal Turing tape, and it moves from point A to point B one at a time. But the entire bus architecture is organized to accommodate that it's optimized for DMA and vector I/O and scatter-gather I/O. So the only way for the computer to really run and move a lot of data is to be very much so about the proper application of these different economies of scale in the chip, on the board, and over the bus. So these are very ubiquitous today and found in most all PCs and other personal computing devices. So this is a book called Compilers. This is the Aho book, or the Dragon book it's called. This Aho Sethi Ullman. This is a usual classroom text. And it just gives a development of, this is our Backus-Naur format. We're making a finite state machine. It's a real simple Chomsky grammar. And then we have a simple one-pass compiler. And then we always talk about abstract syntax trees. So here it's almost always a multi-pass compiler, because the resources for compilation are not like 1965 anymore, and it's possible to spend a little bit more work up front for multi-pass parsing, just parse about anything, and make these abstract syntax sequences, which make just kind of like these layers of from the source text itself up to various renditions of what is the structure out of that, and then to relate that in terms of the programmatic, the procedural terms, back to the instruction sets, the RISC or CISC instruction sets. Those write the object files, and theoretically, that is the computer and what it does. But this is it's just usually known. This would have been the course book of a class called Compilers or something like that. DSP integrated circuits. This Lars Wanhammer from Academic Press has a great little book about the real-time processes. So when we talk about the general purpose processes, it's like it's interactive. It's possible to say, start this, stop that, schedule this, and do it around. A digital signal processor is basically the idea of the real-time flow machine. It's got a steady rate. It's got inputs. It's got outputs. It's got a steady rate. Operates the same under all conditions. Is the idea of a digital signal processor. And so this gets into a bunch of different ideas, and then the development of pseudocode, which results like the synthesis and the hardware definition languages like VHDL or Verilog, that those end up making it so you can write pseudocode, and then that gets into the bit accurate and the clock accurate with regards to the interactions of chips, of computing units, the logics, that the custom and standard logics, that in the land of standard logics, then all this pseudocode is translated directly to graphical layout that then, according to the inputs and outputs of the pins of these pieces of logic, then the overall synthesis is to put down millions and millions of those on the board, or the synthesis, meaning the synthesis of the layout, that the layout algorithm that chip is the thing. That's kind of the idea of very large scale integration, or ultra large scale integration of the large scale integration of integrated circuits, or systems on a chip, largely of any such sort. And so it's about FT processors and DFTs. So this with regards to all kinds of things like consumer electronics, audio, video. Talks about the VHDL description, and that's sequential, and modified description of two parallel butterfly processes in order to meet the performance constraints. And with regards to a lot, with Tukey, Sandy Tukey, earliest deadline is slack time scheduling. When you get into where in the real-time computing, when something ends up connecting two pieces together that are not rate matched, then they have to have some kind of buffer or queues between them to stack up what needs to go into one so it can drain out before it gets to the other one. And then that has to all be combined in terms of these constant rate algorithms, constant resource, constant rate. and with regards to these various sorts of designs in the real time, which then are usually highly economical because they're fixed and then they can be mass produced. And they are in all kinds of electronic devices. Adders, integer logic unit. Floor planning and placement, this is then gets into parts of synthesis, the layout of VLSI circuits, which is usually, and there's some books here studied about it with regards to layout algorithms, and that's one of the most compute-intensive tasks of these sorts of things. This is a book about the graphics card. So Ferraro's Programmer's Guide to the EGA, VGA, and Super VGA cards is quite most definitely out of date. It's from like 1995 or something like that. And so when programming to the PC, without having some of what were kind of the closely held instruction set manuals of the PC, so besides the chips and their instruction manuals, and so for the Intel chips, the ARM chips, you go to their websites and you get their programmer specifications, their PDFs. They have thousands and thousands of pages, but at some point in time they'll have the list of the tables of the instruction sets, and those are they only have like 50 instructions to carry about in the ARM chips, and there's only like 200 plus instructions on the Intel chips, the reduced instruction set and complex instruction set. Then they have the register models, which is like how many registers are there, what's their names, and which ones work with which operations according to these instructions to execute the operations. And then there are some levels of the chips, various things to do with like the rings or the protection levels and their operating modes, plainly. And then other stuff to do with how they communicate over the bus, then is matters of the bus. They used to call it like North Bridge, South Bridge, and with regards to those being kind of standardized chipsets. Audio, video peripherals, user input elements, any kind of peripherals, wireless in the radio, network interface, some kind of at the level of the system, some at the level of the peripheral arrangement. These are all just kinds of usual things that work so simply together because it ends up being kind of simple as to how it is. And so it's not too complicated overall. So then at some point in time, the PC architecture, like the PS2 and all its successors, was built upon these well-known locations of the interrupts, which are control codes for the overall system, that the system integrator would put together a system, and then these interrupts would work usually. And so then a lot of that, in this case, has to do with the video card and getting input and output or handles to the video display. And so these days, that might be as with regards to something like the UEFI's services, providing a frame buffer for the simply kind of thing. And then for the higher graphics card integrations, that gets involved, and there's a lot of proprietary stuff in that. Yet as well that they're mostly bog standard and very similar and much do the same thing. But what this book gets into is all kinds of algorithms and descriptions of the codes. So there was an interrupt list called Brown's interrupt list, Ralph Brown's interrupt list. So when writing for the PC, you'd have to find books like, the undocumented PC or that list was on the internet, and it's a very critical component of trying to write code for those systems, and if not so much today, like this very day, still for systems that are alive today, given, for example, that some of those systems from the 1960s are alive today. That this book is particularly concerned itself with graphical output or the video. And so it's a really great kind of resource to get to figure, because then any kind of modern community or commodity PC these days will still have essentially SVGA and then its later derivatives after XGA and then extended VGA, that this alphabet soup kind of arrives at these standards that for the modern like 4K or 5K, for example, display as of the graphics and the being on board and stuff like that, they're driven according to following this sort plan. And then in the land of the interrupts before the system surfaces, it's just like these given particular interrupts, and then just some code to know that, like, then it also gets into like graphics algorithms themselves, vis-a-vis just like the resource that is a graphics adapter, and stuff like raster ops and this and that. So it gets into stuff like line drawing and font, some of the fonts and outputs. And it describes that the interrupts calls are also called just BIOS calls, basic input output system. And then it gets into like digital analog controller, memory addressing techniques, and these kinds of things. And with regards to the graphic cards of the day, then also it has a great collection of the variations in a bunch of different graphic cards, so that the author provided libraries that provide hardware extraction layer. So that with regards to the very many various modes of the display drivers and the displays, that they could all be kind of treated as one thing, and still as maybe so today with regards to Super VGA. So it's a bit historical, yet at the same time advises the history of it's a largely, it was and has been a largely backwards compatible stack, and it kind of is, certainly. This one's called Operating System Concepts by Silberschatz and Galvin. And so if Finkel there was from 1986 or so, say, this is from 1994, and he says, he's talking about Sun Microsystems, Solaris 2, Windows NT, IBM OS 2, Warp, Mac OS, DEC VMS, TOPS 20. And I don't know so much about like digital True 64 Unix or HP UX, the flavors of Unix, Solaris, Sun OS. I don't know so much about them. B OS, that was a great thing compared to like Commodore, then Amiga, operating systems. The Atari 16-bit, 8 and 16 bits, programmable computers. The BOS was largely held up to be like the coolest thing that was ever going to be. And compared to things like real-time Linuxes or QNX, Neutrino, Plan 9, Darwin as after Next Step in the Mac OS. There are many operating systems, and their internals are kind of well explored compared to something like Windows 7 or something like that. I've looked through the source code of Windows 7, and it's quite a bit. Yet a kind of simpler headless computer could be a lot less. And then with regards to designing that to make like images for running computer elements on the internet, well, it's got to have some. It's got to meet the internet standards, and then it's operational. These kinds of things. As prerequisites, we assume that the reader is familiar with general computer organization and a high-level language such as Pascal. So here the high-level language can just be the language of these terms, and then the general organization is this process model and resource model, pretty much. So the contents of the book are an overview, process management, storage management, protection and security, distributed systems, case studies, the Nachos system. Nachos is an educational operating system. And in this 4th edition, there's just some description of the changes. It's being used for a course. And then otherwise, with a bit more focus on the distributed, that otherwise this is very much similar otherwise to the contents is relevant to the Finkel's walkthrough. But it's got its own tome here. It's collected together. It's like this. Kerberos. This is a description of a distributed synchronization system. So Kerberos is Cerberus is the 3-headed dog at Hades, and so it's a creature from ancient Greek mythology, And so Hades is the underworld, and Kerberos is the guard dog. And it's a weird looking dog because he has 3 heads attached to one body. And they're all looking in any different ways at any given point in time. So he's very hard to evade, or it's the thing. But what Kerberos is that out of MIT came a couple great things for sure. And at least one of them was the network file system after the Andrew file system. This is a way to have files kind of over the network. So it's like, well, my system treats files as according to this file driver because that's the only way we could have fast enough disks for file-intensive purposes. It's like, but really, all we really want is the logical model of the abstraction of durability. And if that lives on the network, I don't care as long as the network is reliable. And so the network file system is one of those kinds of things. And then in the land of distributing and distributed computing and stuff, it gets like, well, can we trust the sockets? No. How about secure sockets? Or like SOCKS, it's called. SOCKS v5, as an example. In the OSI, Open Systems Interconnection 7-layer model of computing and distributed computing, of the physical layer up to the network layer and then the application layer finally, there is a place where up in the application layer, then Kerberos is a protocol so that given computers can connect to a third party that they trust, and then that third party can distribute to them these various ways to go about being able to rely on trust according to some cryptographic principles and some models of the behavior of communication of a protocol, that it's not really possible without breaking the protocol to break into the system. And that by keeping to the protocol, it's well defined in terms of these distributed computers, with the notion that there's like Murphy's Law, whatever can go wrong will go wrong, and something like Postel's Law, which is, you know, be tolerant in what you accept and be vigilant in what you omit, this kind of stuff. That this is just an example of a book that's about the particulars of Kerberos compared to something like these days you'd have redirect flows at the application layer like OAuth or some of these in the land of authentication and authorization protocols with respect to controls vis-a-vis not so much the naming and directory but the naming and directory of controls and permissions, admin and the box and these kinds of things. With regards to the names and the realms and the principles, those being the identities, and then as regards to, for example, public key extensions or smart cards, shared secrets, one-time passwords, and these kinds of things, which can be making it possible that because most protocols for authentication and authorization are designed to run over and across proxies and gateways that can impersonate each other, and that the protocols are and their standard algorithms, basically in the internet, they always make account for that. It's like we have on purpose that a man in the middle can sit there, that setting it up so that computers on the internet can actually trust each other and trust each other for themselves, is kind of a special purpose kind of requirement, because it's not built into otherwise the thing that what protects people's credit cards when they're shopping on the internet is just because they pay so much more insurance money to prevent the almost inevitable false failures and frauds that happen to infiltrate via DNS poisoning and route poisoning and proxy poisoning and man-in-the-middle attacks that can readily convince, given the breakdown of any of hundreds of public certificates stuffed in everybody's browser trust store, that it goes to show that then there, besides though the application layer programming over the internet with all over port 443, say, that there's many other things that go on with regards to what those are and why and how they should be with regards to well-defined behavior given a possibly adversarial or antagonistic sort of network situation. So that's what I thought to look at today, was these books on computing. Let's see here, it's just something a little enriching. This is an Rudolf Arnheim's From Psychology of Art, Visual Thinking. Visual Thinking by Rudolf Arnheim. Has a color plate. Pictures, symbols, and signs. Models for theory. Vision in education. Needless to say, this type of abstraction is a cognitive performance of high complexity. Persistence of shape, just as that of size, may be perceived in ways. Distortion calls for abstraction. This is pretty famous among theory of art, say. In touch with experience. In our own midst, persons of little schooling often think in a way that Frank Riesman, speaking of the style of the so-called deprived child, has summarized as follows. Child is physical and visual rather than aural, content-centered rather than form-centered, externally oriented rather than introspective, problem-centered rather than abstract-centered, inductive rather than deductive, spatial rather than temporal, slow, careful, patient, persevering in areas of importance rather than quick, clever, facile, flexible. So here we'd think to Wertheimer's productive thinking. And here with regards to the deductive accounts, it's true, and it's the principle of sufficient and thorough reason. These are to be cultivated in learners to make stronger learners. Well, gentle readers, I shall so hope you had a great day today. Today is a little bit about computing walkthrough. And so then what I'd look to carry on with a bit more about Quine and then Descartes. I was going to relate those a little bit. And then with regards to the study of the medieval philosophers, then there's been quite a bit of reading, because after the 1200 to 1400, which is from a few episodes ago, of the medieval philosophers, then it gets into quite a bit about the time of Francis Bacon. Now, you may or may not particularly care for Francis Bacon, and you might consider him kind of an effusive, grandiose flake. And it may or be so that found in Francis Bacon's waste book were otherwise writings only attributed to William Shakespeare. It's not so relevant. But at least one point, Bacon does make some good examples of wider things that then are later simplified too much. And so whether or not he can't really be said to hold to anything, there's just some reading from not Roger Bacon, who's kind of got some particular things besides the alchemy and stuff like that, which are non-scientific anymore, although they have the concepts associated with them. That then from the 1400s, or the 1200s to the 1400s, the 1400s to the 1600s, was just some more reading about the philosophy and then of science and this kind of stuff, of the Renaissance and the Enlightenment, for one today, and it's a Renaissance Enlightenment. Hey, have a great day.